Okay, now that I have your permission, Sean, I can get started. All right, thank you. Okay, our chapter 14 notes. And I just noticed this here. We got that going on. So our chapter 14 notes, I tried to make these more succinct so that they go quicker than in the past. Let's do some basics right up here at front. Okay, so something is defined as random if the outcome cannot be anticipated. So that first event or that first outcome cannot be anticipated, but in the long run, the relative frequency, it actually settles down to a consistent and predictable amount. For example, a coin toss. Okay? If I toss a coin, can you tell me what's going to happen on that coin toss? No. But in the long run, can you tell me what probability or the percent of times that it'll land on heads and tails? Yes. Okay? All right, so probability is that long run relative frequency, which we know all sum up to 100%. They all sum up to 1. And then their complement is the probability that the event will not happen, so it's 1 minus the probability that it does happen. Okay, I think those are basics that you already know. So now let's talk about disjoint and independent. Okay? All right. Disjoint events cannot occur at the same time. So they are something that cannot occur at the same time. If you were to draw a picture of them, they would look like this. Okay? No overlap. They are not joint. Not joint. Okay? Another word and vocabulary that gets used to be the same thing as this is mutually exclusive. So they are just exclusive to themselves. They do not have overlap of any sections that they share. Okay. All right. So if one happens, then the other one does not. That is guaranteed. So what happens is this chain of events changes the probability of the other item happening, which causes the probability to change. Then this contradiction of this to the definition makes it such that they are not independent. Okay, so that's where we're headed with this. Let's talk through that. Do you remember our independent? Independent. What does that mean? The fact that you are one thing does not change the rate. Okay, so independent events mean that the fact that something has happened does not change the rate. I actually think it would be better if we go ahead and go through that example first. So turn the page to the independent example, and let's do that one first. So independent events must be able to occur at the same time. So they would have some kind of intersection because you are checking to see if there is an influence on the other, okay, in the event that one of them occurs, okay? So, independent, when the fact that you are one thing does not change the rate. So, if one happens, it has no influence on the other happening at all. The occurrence of one event provides no information about changing the probability of the other. So let's go through this example. I have a deck of cards here. And just to make sure that everybody knows, because I really have had this happen before. I think some people just don't play cards with their family or don't ever mess with a deck of cards. Okay, so what's in a deck of cards? It's made up of 4 suits. 2 of the suits are red and 2 of the suits are black. The 2 suits that are red are what? Hearts and diamonds. The 2 suits that are black are spades and clubs. Okay, puppy dog paws. Okay, and so then how many cards are in each one of those suits? 13. 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king, ace. That makes 13 cards. All right. So what I'm going to do is pick a card, or I'm actually going to, let me shuffle the cards here. And then I'm going to ask Andy. He's going to get to pick a card. Actually, you know what? Let's bet on whether or not you think the card is red. What do you bet? What do you choose to bet?
Yes.
You say it's going to be red. Okay. So he bets it's red. We'll bet your whole stamp sheet.
All right, that's like 3.
Okay. That's like 3. Um, so then if it's red, then you'll get double. You'll get your stamps back. Okay? And I'll shred it if it's black. Okay, this is fake. I won't really do that because it's not going to everybody else. But we'll just pretend it's for real because stamps really matter in here. Okay, here we go. So pick a card, but do not look at it and hand it back to me. Go.
Don't look at it?
Yeah, do not look at it. You got to give it.
Okay.
Yeah, just pick it. Okay, don't look at it. Okay. I look at it. And I'm going to give you some more information, and then I'm going to let you reevaluate your bet. Okay, here's my new information. It's an ace. Okay, so what does that now do to the probability of it being red? Yes, it did nothing. So the probability of it being red is still 1/2 because half of the aces are red, just like half of the deck is red. So the fact that it's an ace does not change the probability of it being red. Okay? All right, so this doesn't help you. The probability of it being red, given that it's an ace, is still 1/2. So the probabilities did not change. Therefore, the probability of being red and the probability of being an ace are independent events. The fact that you are one thing did not change the rate. Okay, so independent events, no change in the probabilities. So let's go back to that disjoint situation. I have another picking a card scenario. So let's go back, because I want to explain to you why disjoint events that cannot occur at the same time are not independent. Okay, disjoint events are not independent, and I want to explain why. Here we go. I'm going to shuffle the cards again. We'll let Kate pick this time. But Kate, I do want you, it was.
Yeah.
Kate, I want you to decide if you want to bet red or not red, okay? So your whole stamp sheet is up for grabs. Okay, she thinks it's red. So pick a card, but do not look at it, and then you gotta give it back to me. Okay, so she picked a card, and then I'm looking at it, and guess what? I am going to give you more information, just like I did with Andy. But the information I'm going to give you is that it's a spade. So then, do you want to change your bet, or are you good with your situation? Okay, so now she changes her bet. She changes it and she says, it is black. So what just happened? When I told you it was a spade, what happened to the probability of it being red? It went to 0. So guess what happened to the probability? It went from 1/2 to 0. Therefore, the probability just did what? It changed. If the probability changed, are they independent? No. Independent events do not change. But here, the probability changed. It went from 1/2 to 0. Therefore, since the probabilities change, by definition, those disjoint events are not independent events. Okay, so that's one new major concept, vocabulary-wise, and those are the examples. So disjoint is the example, red to spade, disjoint, and then the independent example is red and ace. Okay? All right, so let's move on. Let's fill in our little chart here. Let's draw a picture of disjoint events. What would that look like? What you going to have? Two separate circles, not joined. Not joint. Okay? If things are not disjoint, then guess what they are? They are joint. So what would joint events look like? They would have some overlap where you could have A and B at the same time. You would have some intersection. Okay. Now, in chapter 14, our information is very basic. You have these disjoint events where they're separate from each other. And so we do have this basic addition rule where the probability of A or B, addition is going to be the or word, is just adding the probability of A happening plus the probability of B happening. Okay? But here, we're going to have something different, and we'll attack this little box, this little situation in chapter 15. So we're kind of not there yet, really. But this would be where if I say the probability of A or B, yes, it starts out at taking the probability of A and adding to it the probability of B. But I want to draw a picture of that. Here is the probability of A. I just colored it green. And here comes the probability of B. I'm going to color it red. What do you notice has happened? They overlapped. So this middle section got counted what? The middle section got counted twice. So if I just add probability of A plus the probability of B, I have too much information. I have overlap. So I would need to take off one set of overlap. That's the A and B portion. I need to take away one of those overlaps because it got double counted. All right? We'll start this when we do some Venn diagrams, and we'll do that start on Thursday. Okay, next, union notation. Union is going to be or problems. Intersection will be and problems. So our union is going to be when I say the probability of A or B is the probability of A union. And I know that y'all have been using some of that in your pre-cal or your notation in there whenever you were doing domains and stuff. Probability A union B, and that's easy to remember because it looks like a U, so that's nice. Let's do intersection with the and. Probability of A and B will be written probability of A, and then you got the upside down union, and that represents and. And here's the way I remember that. Of course, U is for union. I also think of it this way. Yep, this is your and. Okay, I don't know, I'm a visual person, and so I like to look at visual ways for me to remember things. Oh, okay, nice. So if you say this looks like an N, like a lowercase n, like intersection. Okay, so either way, however you choose to remember it, remember it. Okay, last part of this. Explain the difference between union and intersection. I want us to draw a picture of what the union and the intersection would look like. So here we go. Probability of A union B. If we have overlapping, we can have overlapping events for both. Okay, and then we're going to draw this one, probability of A intersect B, and draw the same picture, and then I'm going to shade what they mean. All right, so this first one, the union, what part of that picture do you think I mean? When I say union, what part of this picture will I count? You will actually count A, B, as well as the A and B. So all of this section, it can be A, or it can be B, or it can be both. So it can be A, or it can be B, or it can be both. Okay? But over here, where it's the intersection, I think you guys know that that is only the part that is both. All right. So that's usually kind of new. I think when we say or, we want to mean exclusively or, but it technically does include both as well. All right. Next. In this chapter 14, the very first one that we're starting with, all the events are independent, which is nice. We're going to get the easy ones over with, get kind of a review of the probabilities we've done in school up to this point. And so we would just multiply the probability of A times the probability of B. Okay, here's an example. Find the probability of flipping a coin and getting heads 2 times in a row. So are those independent events? Does the fact that you get something on the first flip affect the probability of you get something on the second flip? No, so therefore they're independent events. And we want to get heads on the first flip and heads on the second flip, so what's the probability of heads? 1/2, and the other one is 1/2, so the probability of getting heads 2 times in a row is 25%. Okay? Now I want to demonstrate that to you with a sample space of like all the possibilities. Sample space would be all the possibilities. What are all the possibilities of flipping 2 coins? Or 2 coin tosses? Okay, so those are all your possibilities. So there are 4 possibilities, and how many of them had exactly heads? 1 out of all 4. Therefore, that was why the probability was 1/4. Okay? All right. Now, the next thing I want to teach you is a keyword and how to do it how to find the probability when it asks you for at least one event happening. So you're going to remember this, that the probability of at least one is 1 minus the probability of none. The probability of at least one is 1 minus the probability of none. Okay. I actually wish that I had put another example in here about just flipping the coin twice, because I want to demonstrate that again. I want to first do this simpler so that I can physically show you what's happening, and then we'll do that problem with the 5 coins. Okay, so I want to ask you, what's the probability of, of flipping 2 coins and getting at least one of them are heads? Okay, so I want to demonstrate our method that says 1 minus the probability of none of them are heads. Well, what does it have to mean for none of them to be heads? They are both tails. So that would be, tails, tails. So that's 1/2 times 1/2. So this is 1 minus 1/4. So what's the probability that you get at least one heads? 3/4. Okay? Well, guess what? Watch this. When we did our solution set, what's the probability of getting at least one heads? 3 out of 4. Okay. So what we did was we took everything and then just took away the tail, and that left us with 3/4. All right, so let's do that with something that's more difficult to draw out, which would be 5 coins. I would hate to draw that sample space out. That would be 120 different sets I would have to draw, okay? And I'm not going to do that, okay? So because I know that the probability of flipping 5 coins, or probability of flipping it 5 times and getting at least one heads, at least one is my key, that would mean 1 minus the probability of none of the 5 coins are heads. It's everything except all 5 of them being what? Tails. In order to have at least one head, I have got everything except for all 5 of them being tails. Just like here. In order to have at least one heads, I have everything except for both of them being tails. Okay, well on the other thing, I've got everything except for all 5 of them being tails. So that's going to look like this. 1 minus, you don't have to draw this out because but I'm drawing it out for you. All 5 of them being tails would mean a half times a half times a half times a half times a half. That's all 5 of them being tails. So you're essentially saying 1 minus 1/2 to the 5th power. Okay. All right. Did you follow that? 1 minus the probability of none of them being heads. At least one is 1 minus the probability of none. Which, by the way, if you put that into your calculator, it would look like that. 1 minus 0.5 to the 5th power. And that means there's a 96.88% chance that you're going to get at least one heads when you flip the coins. Which, doesn't that make sense? Seems like it should be a pretty high chance that you're going to get at least one of them being a heads. Okay. All right. Let's have you try numbers 1 and 2, and then we'll check them. Okay? So try that. Do you know what? I want to change the problem number 2. It really isn't going to change your math, but I want to change this word 5 to a 2, because the way that it works out, it could be confusing to somebody if I left that as a 5 as to why I chose that 5. But let's say for number 2, what's the probability of rolling 3 fair dice and having at least one of them showing a 2? So at least one caught my attention. So at least one of them showing a 2 means 1 minus the probability of none of them showing a 2. Okay? So not a 2 times not a 2 times not a 2. And what's the probability of not being a 2? 5 out of 6 times 5 out of 6 times 5 out of 6. So whatever that ends up being mathematically is your answer. Okay? Did you do all right on that? Okay. All right. Well, if you did all right on that, then do number 3. Okay. So 1 minus at least 1 being a vowel would mean 1 minus the probability of none of them being a vowel. Okay, so what's that mean that I got? What's the probability of not being a vowel? Okay, 2 out of 5 here, and then how many in the next one? 4 out of 6. Okay? So I'm going to take away all the ways that the vowel could happen. Okay? No, I mean, you're going to get a probability in the end, so that's okay. I mean, so you would just get a decimal, so the reducing wouldn't matter. All right, good. Questions there? Okay. Now we've got a Venn diagram, and we're going to spend a lot more time on Venn diagrams on Thursday, but here's a pretty straightforward one. And so let's let you look at that. First, notice that we've got the A portion is 0.4 by itself. Total A, however, would be how much? 0.5. Okay, 0.5 would be the total A. And then we've got the B by itself as the 0.3. What would that mean is left over here on the outside of the circles? Yes, because we got in the circles 0.8. So outside the circles would be my 0.2. All right, so I want you to try these ones here, and then we'll see how you do. Just the whole B circle is what you'd be looking at, everything that's contained in the B circle. Okay, so on part C, remember the complement is 1 minus the probability of A and B. Okay, because the complement is everything else other than that. So what portion of this picture is A and B? It is this 0.1 in the middle. So I'll do 1 minus the 0.1 in the middle, and that means everything else other than that intersection is the complement of that intersection. Okay? Now, D can be done a few ways, and I could actually show you the picture part, and I'm going to here in a second, but I think it's a little more confusing than just saying the words out loud, and it seems a bit more natural and makes more common sense that way. So let's say these words out loud. Find the probability that you do not have A and you do not have B. So I want the section that is the not A and the not B section. Where would not A and not B be? Outside of the circles. So therefore, how much is that part? The 0.2. Now I want to show you, I'm going to shade that and kind of quote unquote prove it to you. So I'm going to do the intersection of the not A and the not B. So first I'm going to shade not A. Okay, here's A. And so then let me do not A. Okay, here's the not A. Okay, so there's not A. All right, next I'm going to do B, but I'm going to do not B. So here is B, so I want to do not B. So here's the not B. Okay, and what does it tell me that I want of those two places? I want the intersection of not A and not B. Where is the intersection, the two colors? On that outside edge is the yellow and blue. So that's the 0.2. Okay? All right, there's the picture version. All right, last one I want us to do, see if you got this before you start doing this on your own. So, one more practice. Here we got 5 multiple choice questions, and they each have 4 possible answers. So I want you to, here's the story. You go take a history pop quiz, and they are A, B, C, D answers, and one of the answers is correct. So you just got A, B, C, D. How many choices are right? If you randomly guess how many choices are right and how many choices are wrong, 3 out of the 4. Okay, so 1 out of the 4 answers on a problem, 1 out of the 4 answers is right, 3 out of the 4 answers is wrong. Okay? All right, I want you to try those problems right now. let's go ahead and take a look at some of those so far. So if you get none of the questions correct, what does that mean about all 5 of them? They are all wrong. So all 5 of them are wrong. Wrong, 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 wrong. So that's 3/4 to the 5th power, whatever that comes out to be. Okay? How would that work if you get all of the questions correct? Then that means correct, 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 correct. And so that's 1/4 to the 5th power. Okay, so A is not a 1 minus situation because it's straight up saying that absolutely none of them are correct. It did not say at least one of them is correct. It would say at least one of them is correct. Okay? So, in fact, this one is, part C, is an at least one question. So if at least one question is wrong, then that would be 1 minus the probability that what? None of the questions are wrong. 1 minus the probability that none of the questions are wrong. Okay, so what would that look like if none of them are wrong? Isn't that they're all right or all correct? Which we saw right here. So it's 1 minus 1/4 to the 5th power. All right, now D we haven't seen before. It actually lays out the order in which these things must happen. You got your first problem, your second problem, your third problem, your fourth problem. It defines. You get your first incorrect answer on the 4th question, so this 4th one is wrong. What does that mean about the ones in front of it? They were correct. So that defines the order as a 4th, a 4th, a 4th, and 3/4. Now what you going to do with this last one? Who cares? You could leave it off completely, or they just answer the question, whatever they get it right or wrong, it doesn't matter. You could put a whole number 1 there. Doesn't matter. They haven't defined what that is, so you can just leave it off. And then that would be how you get your answer there. Okay? All right, now, the law of large numbers is the next thing that we would do. However, we're going to skip that and save it for tomorrow. So turn to page 7 in your packet, and let's look at the first assignment. You are going to skip the first problem, which is number 7, and you are going to skip the second problem, which is number 8 for now, because those have to do with the law of large numbers, which we'll do first thing tomorrow. Okay? But let's take a look at that number 9. I just wanted to explain to you that this is actually not a multiple choice option. It's 5 different scenarios. So it says, a plastic arrow on a spinner for a child's game stops rotating to a point at a color that will determine what happens next. Are the following probability assignments possible? Why or why not? If you say yes, it's okay. Just say, if you choose no, tell me why it's not. For example, question A says 25% are red, 25% are yellow, 25% are green, and 25% are blue. Is that a possible scenario for a spinner? Yes. So what kind of qualities would I be looking for here on these probabilities? Total to 100%, okay? That the 4 colors together total to 100%. Anything else that looks kind of striking of those? Yeah, you probably shouldn't have a negative probability. I'm kind of thinking probability can't be negative. All right, so you're going to be saying yes or no on those parts, A, B, C, D, E, and then if it's a no, say why. And then you'll do the rest of that through page 10. So your assignment is pages 7 through 10.